auspicious BCTCS Maths Day. We're very fortunate to welcome Tim Gowers, who's come down the road from Cambridge. Tim is best known for his work in Banach spaces, but I guess some people in the room might know better his work in combinatorics. But today he's going to talk about his ideas in automated theorem.
Thank you. When I received this invitation, I felt slightly sort of embarrassed about it because I'm sort of coming into a room full of people who know more about automatic theorem proving than I do. And I don't really, in addition, although I'm very, very interested in it, I don't have that much to show for myself. So I'm not going to talk about a spectacular achievement like solving a centuries-old problem and then formalizing the proof. I'm not really even going to talk about a sort of humdrum run-of-the-mill achievement. I just want to try to explain why I'm very interested in this area and the sort of way I want to go about it. But most of what I'm talking about is kind of in the future, I hope, rather than in the past. I did mention in my abstract work with Mohan Ganesalingam, who's a fellow at Trinity and a member of the computer science department in Cambridge, although he also has a degree in maths and very good at maths as well. I'll talk a little bit about what I've done with him at the end, just to sort of justify having mentioned in the abstract, and also to establish in a very weak way some sort of credentials for being here. But really what I want to talk about is just to try to explain the philosophy behind what we're doing, and maybe try to, maybe I'll sort of convince you, maybe I won't, that there is an approach that we have that might have something that other approaches don't have. Having said which, I don't want to suggest that everything's very new about it and that sort of thing. I thought I'll just leave the question of how you do it, I'll leave you to decide how much is things you find new and how much you find very traditional. But before I go any further, let me just try to place where we are in traditional categories. So, in things that often go under the banner of automatic theorem proving, there's a sort of spectrum between checking on the one hand, formal verification and so on, which we've heard a lot about in Thomas Hayward's talk, and proving, i.e. where the emphasis is to try and get your computer actually to find proofs. So checking, at the extreme ends, checking, you put in all the steps, but you just, unless it passes the formal verification, it doesn't count. Proving, at the extreme end would be, you just put in a statement and hope that the system outputs a proof. Another spectrum that's, is that between machine-oriented on the one hand and human-oriented on the other. So roughly the difference is that, I'm not trying to say anything new, I'm sure everybody knows this, but machine-oriented would be, the sort of rough idea would be to exploit what computers have that we don't have, like the ability to make lots and lots of calculations very, very fast and have a huge memory and things like that. In order to do better than humans, and there have been some spectacular instances where that's happened, like the one that's always mentioned, the proof of the Robbins conjecture, which was an open problem and was solved using machines. And finding the proof involved searching through a huge amount of sort of proof space, let's say, cutting down the search in clever ways and eventually finding the proof. Once you've found the proof is sort of actually not that long. A human can follow all the steps of that proof, but the thing that took a long time and needed a big search was just the discovery. Human-oriented is where what you try to do is to say, well, let's look at how mathematicians find proofs, try to understand that well enough to be able to program it into a computer and get computers to find proofs in the same sort of way. But it's a spectrum because you can use some sort of things that humans do to speed up your searches in your machine-oriented things, and also if you're doing a human-oriented approach, you could sort of sometimes use the brute force of computers to cut a few corners and find steps that humans would find in their mysterious human way. So Mohan and I are as far to the human-oriented end of this spectrum as it's possible to be. In other words, we try to outlaw anything from the proof discovery process that a human wouldn't do. I'll say a lot more about that as we go along. But anyway, that's why this talk is called Extreme Human-Oriented Theorem Proving. And then also, this is sort of related to the checking and proving spectrum. Is the system an interactive system, one where you type in some things and you give the computer some help, but then the computer also then takes some of the steps and so on? Or is it a fully automatic one where you just give it the problem to solve and it solves the problem? And our aim was very much to do the fully automatic thing. But if you could, somehow I don't see the distinction as, it's not a sort of black and white distinction, because if you could build a fully automatic system that could do pretty well, it could solve sort of fairly hard problems, but not very hard problems, then you could just use that as an interactive theorem prover. When you're trying to prove a theorem, and you say, well, here's a possible lemma that we might be able to prove, and then your interactive theorem prover could then say, here's a rather simple counterexample to that proposed lemma, and that would save you what might have taken a week or so if you'd just done it by yourself. Sometimes lots of times you can sort of build an emotional attachment to some statement which causes you to spend quite a long time trying to prove it and not spend some of that time trying to find a counterexample, and had you spent it, you could quickly find a counterexample, that sort of thing. But nevertheless, our sort of aim is very much the fully automatic. We don't want to build something that depends on human help. So, one way of summarising, I think, what the sort of philosophy behind it is that the question that really interests us is less sort of how can I build a program that does all sorts of interesting stuff, than answering this question. What is it about human mathematicians that enables them to find proofs with the efficiencies that they do? It's quite a mysterious question. It's easy to check, or easy to prove that the general problem, here is a statement, does there exist a proof of length at most n? That's basically trivial an NP-complete problem. And yet, mathematicians are finding proofs of theorems the whole time. Obviously, the answer to that is partly that we don't try to find arbitrary proofs of arbitrary statements. So we're not actually solving NP-complete problems in polynomial time or something like that. They don't have some magic ability. But what are the details of that answer? That's it's not an easy question to answer. So we just maybe make things a bit more concrete by giving it I have a few examples that I want to discuss during this talk. So here's a pretty simple question. You've got a group, you know that AX equals AY, and you have to prove that X equals Y. That's proving the cancellation law. So let's have a quick look at the proof of that. I'm going to try to we'll go right back to the axioms of group theory and various other things, although obviously one could formulate it further than I have done. So we start with that, and then we say there exists an inverse to A, multiply both sides of the left by the inverse, use associativity. Well, actually, a human would normally just use associativity quickly on both sides, but I'm spelling it out rather a lot. So I'll use associativity on the left-hand side, then and then I'll also use the fact that BA is identity, which is the definition of B, get that BAX equals EX, and then E is identity, so EX equals X, and therefore X equals EX by symmetry of the equality. You do the same sort of reasoning on the right-hand side, and then you've got enough equalities there that by using transitivity of equality lots and lots of times you can end up proving that X equals Y. How would a human actually think about it? It would be more like this. You just multiply on the left-hand side by the inverse. Notice I haven't even bothered to put brackets there, because the way a human would think about associativity is more like you just don't need brackets. And a human would sort of just jump straight from there to there, and if asked to justify it, they'll say, well, this a to the minus 1a is the identity, and the identity times a to x. Now, even there, you've got quite a lot of interesting questions at the technical level. How would one get an automatic theorem prover to be able to reason a bit more like this? than like this. So without sort of painfully using all the axioms all the time, but just sort of, and people have written about building in associativity and things like that, so you build it in by just not putting the brackets and so on, having various replacement rules that just sort of, like a human, just use associativity without really thinking about it. But the question I want to focus on really is, well, basically why do we multiply by this inverse of A on the left? It's the obvious thing to do for a human. So here are two sort of different ways of thinking about this problem. So a sort of more machine-oriented person might think, what program could I write that would end up finding that particular proof? I don't really care how it does it, it's just got to end up with that proof. So what you could do is just get it to try various things. Given the initial AX equals AY, one other thing you could do is invert both sides, or you could multiply both sides on the right by A, and all sorts of other things you could do. And you wouldn't have to search for all that long before you'd reach the idea of multiplying both sides on the left by the inverse of A. And once you've done that, you get some quite nice cancellation. In fact, sufficiently nice that it actually solves the problem. So it's sort of, one could imagine that a brute force search would fairly quickly come up with that proof of the cancellation law. But for Mohan and me, that would have been sort of very unsatisfactory. Roughly speaking, because it does all sorts of stupid things that a human wouldn't do. You would not invert both sides and expect to be getting anywhere. So our question is, the question that we would want to focus on in this particular example, is what is it about us that makes it sort of obvious that the thing to do is multiply on the left by a to the minus 1. And the sort of danger in all this is that you come up with an answer that's rather specific to a particular problem in hand and doesn't generalize. So that's why I've emphasized general principles. We somehow want multiplying by a to the minus 1 to be the first thing the computer even tries, because any reasonably experienced human, that would be the case. Just, I think this is a difficult problem. A sort of rough sketch of what I think the answer is that when we do group theory, we draw an analogy, or we have in mind our experience with arithmetic and division, and we think of a to the minus 1 as sort of like the reciprocal of a, and we're very used to the cancellation law for real numbers, and we just divide both sides by a, and so we think, what would be like dividing both sides by a? Well, it should be something like multiplying both sides by a to the minus 1, and then we can sort of quickly see that if you do it on the left, you get somewhere, whereas if you do it on the right, you won't get somewhere. There's some sort of, I think, so that's a sort of rather complicated answer, and not something that's, if you just wanted to write a program, it would be a little bit disconcerting if to write a program to do elementary group theory, you have to sort of build in a whole lot of prior experience with arithmetic and analogies and things like that. But I think, actually, unfortunately, that may be what's going on in our heads. So that kind of difficulty does come up a lot with what we're trying to do. So why bother with all this? It's a very natural thing to say, to sort of attack this, but it seems a bit silly to not to use the very thing about computers that makes them sort of useful. So the whole point about computers is that they do things very, very fast, and they can afford to do big searches, and they have a lot of memory and so on. So, what would be the point in just not using all that? Don't you just end up with something that doesn't do maths any better than we do? Well, one answer is, if you do that, so if you do ban any non-human steps, you'll still have something that's much better than a human mathematician, for the very simple reason that it will be able to do the human steps very much faster than a human. So you can imagine your computer will be able to sort of go through the thought, if you manage to program it to think like a human mathematician, it would be able to do that at vastly greater speeds, so it can try all sorts of things much more quickly. So you would exploit the speed, but the point is that you'd exploit the speed not at every single step of the process. I think that's sort of the main point to make. Slightly more theoretical, but not something I claim as a formal, just to check that I've... Yeah, so one reason I want to say is that there does seem to have been some sort of plateau reached with theorem proving, in that although there have been some impressive things done, and one person I'd like to mention actually just as the person working in this country that I think is sort of closest to the sorts of things that we're interested in would be Alan Bundy and his schools, and they definitely take the human-oriented side of things quite seriously, and they explicitly said that sometimes their aim is not to produce the most powerful program altogether, but just like us, but to produce initially something that might be less powerful, but that has more chance of sort of scaling up. So it just does seem to be that there are a lot of problems, and I'll discuss one or two of them in a moment, that humans find pretty straightforward, and they're sort of well beyond what the best automatic theorem, fully automatic theorem proving programs can do. Yeah, so one of the problems of the devil's odd area is combinatorial explosion. So you're trying to find some object, which is a long sequence of logically valid steps. It's your path from your assumptions to the conclusion that you're trying to prove. If you allow, now this path can be quite long, and not just that, actually, I want to be careful how I put this, not just that the path is long, but the path to discovering the proof can be quite long. So there's two different things to think about here. One is the path in the sense of sequence of logical steps, and the other is the path in the sense of sequence of thoughts that you have in order to discover the proof. So it's more like the second that I'm trying to talk about here. So this sequence of steps that you have to make is quite long. So so that means that you're searching in some sort of graph, and the depth of the search that you need is quite large. So if you're allowed if at each step you maybe even only allow yourself to try two things, then after a small number of levels, it blows up and you're ending up with a search that's not practical at all. So you've got to have some way of cutting it down. And so it seems to us that if you can somehow ban even very simple searches when humans wouldn't do them, then there's more chance of things scaling up. I should say that a small amount of search in theory is okay, as long as you've got some means of deciding if it's going nowhere and quickly backtracking. So as long as you're not going to explore the whole library tree, but you get to here and say, well, that's hopeless, so ignore everything that's down below there. You've got some means of searching a big tree. But backtracking is not forbidden altogether. I mean, you can't forbid it altogether, because humans do a lot of backtracking when they're looking for proofs. But we just want to make it, we want to minimize it, and I think even just being slightly sort of tolerant of more backtracking than humans would do is. This is just a theory which I can't prove, but I think that may be an important part of the reason that automatic theorem provers, fully automatic theorem provers, haven't got further than they have. One other reason that I think is important for me personally, it might not be important for everybody, but what I would like to see out of an automatic theorem prover is something that does more than just say, here's a proof, but actually can tell you how it thought of the proof. And that can be sort of somewhat similar to the way that a human thought of the proof. So you feel that you've got some understanding of the proof. This is a problem with maths literature and human maths literature, that people just say, here's a proof. And then when you're reading a paper, it's very difficult to... sometimes you can understand the proof line by line, but you can't really understand the proof somehow. And I think an automatic system that did more than just say, these steps work, but actually said, well, I tried this, that didn't work because of the counterexample, this assertion here, so I had to try this slightly more complicated thing, etc., etc. That would be much more useful, and I think you have to have a more human-oriented approach to any hope of that type of facility and program. Okay, so I thought I ought to provide an example of a problem, but I don't know for sure, but my guess is that this would be a big challenge for any fully automatic theorem provers around today. If not, my general point is that such problems do exist. So if somebody knows of a theorem prover that could handle this problem, it doesn't completely ruin the point I'm making, it just means I should have chosen a better example. But here is an example that I got off a first year example, or first term Cambridge example sheet. It's quite a well-known question. So can you find 100 numbers, 100 consecutive numbers that are all composite? So I suppose a machine approach might be just sort of do a brute force search, but that will take quite a long time to do. So to find 100 consecutive composite numbers given the density, I think that you'd probably have to search further than that would be feasible. I'm not saying that's how a machine-oriented program would find the proof, but I'm just saying brute force search is not really possible. So let's just think about how a human might discover a proof. And I suppose the main point I'm trying to make here is that this is something that one can analyze in some detail. What I will try to do is convince you that the idea can be generated using sort of moves that themselves are not very, or sequence of moves that are not themselves particularly, don't require sort of huge leaps of insight or anything like that. So things that, although I'm not claiming I can automate all these steps, I think they're things that are highly believable could be automated if enough work was put into them. So, this is just a slightly more formal way of saying what we want. So we want to find an n such that for every r up to 99, n plus r is not a prime number. That's 3, 0, 99. I'll be a little bit sloppy about saying things like r is a non-negative integer and things like that. I just want to, so it's not the proper formalization, I just want to make it slightly formal. Sort of in between what a human would write and what an assistant machine would need. I've made it a little bit more formal here. So what I mean by is not a prime number, I just mean the usual thing. You've got some number that's strictly between 1 and n plus r, and it divides n plus r. And it has to be an integer and so on. So next step. So one of the first things that a human would naturally do, and have to do it, but you might well do it, is say, well, this 99 probably isn't absolutely crucial to the problem. Since it's not crucial to the problem, it's a bit of a sort of distraction. So let's just replace it by some arbitrary integer. So formally we'd be saying for every n, you can find an n such that for every r up to n, a plus r, so n plus r is not a prime. And once you've generalized, these the generalized and specialized steps are two that Poyer wrote about. First generalizing something and then specializing something. They turn out to be quite a fruitful way of going about things. So here, we take a special case. I could have even taken n equals 0 as my first special case, but let's save a little bit of time and go for n equals 1. So now we want just substitute 1 for n, but let's just rewrite that slightly. It works out as saying that we want n and two factors a and b such that a goes into n and b goes into n plus 1. That's what we want for this special case. So there it is again. I'll just repeat the word on the slide. So can we do that? Well, we've still got some decisions to make. This starts with, so most of the problems that arise when you're trying to solve problems at this level seem to come when you've got an existential quantifier, because somehow you've got the whole universe of possible things to choose from, and how do you make that choice? But we've got a number of tricks for restricting the search. One of them is just to try the simplest thing and see whether it works. And in this situation, that seems like quite a good possibility. So I'll break this down more than like that. I could have done it all in one step. But let's try the simplest thing for A. It's got to be at least 2, so let's try 2. And similarly, let's try the simplest thing for B. with a little bit of thought, you see that if 2 goes into n, it won't go into n plus 1, so that rules out 2, so we better go for 3. So we've got 2 to go into n, 3 to go into n plus 1. So that's if this failed, if we couldn't find such an n, that might mean that 2 and 3 were a bad choice, and we'd go back and try some other things. But let's just see what happens. So, because we've now done something, we've made the problem more specific. So we only needed to find A and B. Now we've got down to some actual triangles instead of A and B. And a brief check, we find that the smallest n, such that 2 goes into n and 3 goes into n plus 1. Well, the smallest one is 2. We're not allowed that because n's got to be bigger than 2, so the next one is 8. Then you look at that, and it's not sort of massively helpful because it's certainly not the case that the first 100 numbers after 8 are all composite. But still, we're not done yet. But we still don't quite know what to do, so let's try the next case. So let's take n equals 2. So now we want to find n plus 1 and n plus 2 that are all composite. We go through some reasoning a little bit like what we had before, except that we actually spot that if 2 goes into n, then 2 goes into n plus 2. So actually, it wasn't really a different problem from what we had before. So we try the next one, the next difficult case. So the first time that any trouble arises is when you've got n plus 1, n plus 2 is taken care of if we've chosen a equals 2. So n plus 3 will be the next one. So we simplify that. Actually, it's not really a simplification. I realise now looking at this again. That's a simplification if we assume that we're going to take a equals 2. So then we won't need to worry about n plus 2. So I promise you I'm going to choose a equals 2 again. And so now we see that if you choose 2 for A and 3 for B, you can't choose 2 or 3 for D, so the next, or 4 for that matter. So the next possible one is 5. So we get, can we find an n such that 2 goes into n, 3 goes into n plus 1, 5 goes into n plus 3? I think most humans at this stage would either say, well, yes, you can by the Chinese theorem or something like that, or they'd say, well, I'm not even going to bother to think about that because it looks a bit, just finding one, when I found the number 8, it didn't really help, so it's not likely to double that much if I just happen to verify that something like 28 or not, something works. For this, it's not necessarily going to be helpful. Instead, we sort of prefer to think, what about just sort of trying to generalize what we're doing here? Can we do that? And we find, well, we look at n plus 4, 2 goes into that, so the next one that's a problem is n plus 5. 2, 3, and 5 won't work because they're all sort of spoken for, so we'll need 7 to go into n plus 5. And now at this point, we start to notice something that 2, 3, 5, and 7 are the first 4 primes. And 2 goes with n, 3 goes with n plus 1, 5 goes with n plus 3, 7 goes with n plus 5. So it looks as though each condition is a form, take a prime, and it goes into n plus that prime minus 2. And at that point, we can just think about what we would want. And we're interested in all the numbers from n up to n plus m, so we only would need the primes up to n plus 2. So it seems reasonable to conjecture at this point that we'll be okay if we can find an n such that all the primes, for all the primes up to n plus 2, we have that prime p divides n plus p minus 2. It's actually pretty easy to check that that is indeed a sufficient condition, and I'll leave that bit out, because I think that's a significantly easier problem than the problem we started with. So I just called it a straightforward argument. It's an argument that is more believable that the computer could discover than the argument we started out with. So sort of by induction we're done, something like that. So the general statement that we want is this thing here. So now I've got another standard move. We simplify things. We notice that p divides p minus 2, if and only if p divides n minus 2. So we need all those primes up to n plus 2 to divide n minus 2. Can we do that? Well, that's again a problem that's significantly simpler than the one we started with. If you want a number that's divisible by a whole bunch of primes and just multiply those primes together. It is not 100% straightforward to work out how a fully automatic system would solve even that simpler problem, but it is simpler, and I think it's much more believable that with ingenuity that can be done. And I have thoughts about that, but I just don't want to dwell on that. Because, the thing I'm dwelling on really is that we've actually solved the problem now. The answer is we wanted an n such that the 100 numbers from n onwards are all composite. So all we have to do is make sure that n minus 2 is a product of all the primes that are less than or equal to 102, and we solve the problem. So if I just said, say an undergraduate came to a supervision and said, I tried to do that problem, I just couldn't do it. And I said, well look, if you take n minus 2 to be the product of all the primes that are less than or equal to 102, let's just check that that works, and gone through a little sort of verification that it works. That would leave them thinking, yes, okay, I can see that that works, but how did you think of that? This is a common complaint. How did you think of choosing that number in the first place? And this is just one way that it might be done. My firm conviction is that similar sort of just so stories, so to speak, can be told about pretty well any mathematical advance. So any mathematical advance, bar the absolutely sort of lowest level simple ones, can be broken down into smaller advances. Or enough smaller that, I don't want to say that they sort of converge to some, no, that's not quite for the heavens. They can be broken down into smaller advances, and so eventually down to something that's small enough that it can be automated. And I also think the process of breaking down can be automated. So I feel that there is, so that's the sort of conviction with which I go into this, that I feel as though when I'm thinking about maths, something systematic is going on. It sort of looks unsystematic from the outside, but for no reason for it looking unsystematic, but fundamentally it's a sort of systematic process, I think. I want to talk about another example because it will illustrate something useful later on. So this was the next question on the same question sheet from the one before. So this time we're trying to find, we're thinking about sequences of prime numbers. So we've got this sequence here. This is another quite well-known question in the right circles. So the rule is that you start with 41, and you add 2, then you add 4, then you add 6, then you add 8, then you add 10, and so on and so forth. And the question is, are all those numbers prime? This turned out to be an easier problem. I'll just quickly talk you through it. I don't mean talk you through the solution, but I'll talk you through the sort of finding the solution process. So, first of all, this one would be easy for a computer to solve by brute force, because the answer is no. So the computer can, in no time at all, just sort of test the first few terms of the sequence until it eventually finds the prime. But it turns out that the search it would have to do is long enough that although a human could also do it, it would be very, very tedious. Much better for a human to try to look for a theoretical argument. But anyway, the natural thing to do for a human would indeed be to start with a brute force search and just see what happens. So if you do, you find the next few terms, 71, 83, 97, 131, 151, all of those are prime. So it sort of looks kind of as though the answer might be yes, but on the other hand, just because it's yes so far, it's not very strong evidence for it being yes all the time. So, having sort of got exhausted by the brute force search, the next thing to, I think is a very natural thing to do would be to find a formula for the